It's coming back up. So welcome, this is interference of light waves. So now we're talking about light as a wave as opposed to a particle or a ray. So you can think of a ray as being like this continuing stream of energy, or you can think of it as being a whole bunch of little bullets of little wave packets. Either way you choose to think about it, what you do is you get some really weird effects. If I just shine a light on a wall, I'll see a disk of light, bright in the middle and dim towards the edges. If I put that light through a slit, then I start seeing some effects. If the slit's not very narrow, then I don't see much, I just see a bit of collimated light. If I make the slit narrower and narrower, so that the width of the slit gets on the order of the actual wavelength of light, that's not that small. I mean, the wavelength of light is quite big, 400 nanometers for blue light. That's 400 times 10 to the minus 9 nanometers, which is 4 times 10 to the minus 7, which is 0.4 micrometers. Micrometer is quite big, actually. So light is quite big. The actual wavelength of light is quite big in the visible range. So if I start getting a slit on the order of that, I'll see some weird effects, and they're called diffraction effects. There's also interference effects. And interference effects are where you get two sources of light interfering. And we're going to start with interference effects, and then we're going to talk about diffraction effects. So what's going on here? So first of all, what are the conditions for interference? Interference, the sources of light must be coherent. That means the crests and the trough must be in sync with each other. Okay? So if I have coherent light, everything lines up. If I take a snapshot, and that's if you had a continuous stream of light, that's what you'd see. If it's made of wavelets, then let's see if I can draw it. It's got to line up. And you might have another one here, and it's got to line up. And these guys have to be in the right relationship to each other. So this kind of continuous wave. It's like you might have individual soldiers, but they are in step. You know? Imagine the ranks of soldiers all marching. All right, do the same thing with only 10 soldiers spread out. They've just got to be in step with each other. That's coherent. They are in step with each other. If I just take a normal incandescent light bulb, each photon is its own thing, and they've got no relationship to each other. They're just there. So sometimes you're getting a crest when you should be getting a trough, and sometimes it's a bit of a crest, but not the full crest. So coherent light is when it's nicely in step. Lasers give you coherent light very nicely. Source must be coherent. Monochromatic. Chromatic meaning kind of colour. Monocolor. One wavelength. One frequency. And they've got to obey the superposition principle. What that means is if you take one and add it to another, you go 1 plus 1 equals 2, or 2 plus 2 equals 4. It adds arithmetically. We had some of this for sound, actually, yeah? Because we did interference of sound, so we're back here. But you can do this with light. This is amazing. And back in the day, so Thomas Young did a famous double slit experiment. He did not have a laser. So how on earth did he get coherent light? What he did was he took a light source and he basically put the light source, which has light streaming out in all directions, put the light source through a single slit. And that single slit then acts like, remember Huygens principle, you get wavelets coming out. And they are, by their very nature, coherent. They're in step with each other. So he made coherent light out of normal light, incoherent light, by using this first slit. So you have coherent light reaching these two slits, and then what happens? And what happens is you get this most amazing thing where, lost my pen. It's the most amazing thing where you get this pattern of dark and light fringes. Now imagine that you're stood here in this apparent shadow. There's nothing between you and this first slit, and there's nothing between you and this second slit. So you're seeing darkness, but two light sources are shining on you. It's like, hold on. Light can cancel light and give me darkness. Yes, it can. And it does. And that just is kind of strange, isn't it? If you think a light has just been bundles of energy, how can two bundles of energy give me no energy? It's like, it just seems very strange. But it's well documented. It happens. I can show you in the lab. It happens. Okay, there's a certain geometry to this. What you find is that depending upon where you put the slits, if you put them close together, then these fringes spread out. If you put them relatively far apart, the fringes collapse. So you can play with the geometry. So we need to do two things. We need to sort out the math, and we need to sort out the nomenclature, the wording, because we've got some new things to talk about. So what we say is basically the two slits act as a pair of coherent light sources. There's that word coherent again. We get a pattern of dark and light fringes. So these are fringes that depend upon the difference of the point's distance from each of the two slits. Path difference. Primarily, well, it is completely path difference in this effect. How far am I away from one slit versus how far I'm away from the other slit? Because the two slits are in phase. Remember that when we talked about speakers being in phase or anti-phase? Clearly the two slits are in phase because they're coherent. Now the distance between them, that's a different issue. We identify the fringe by its order and assign an M value. And I've got to be honest, I have one equation and I mess with the M value for light and dark fringes, and the book has two equations, and they have a simpler M value. So I prefer my way, they prefer their way, but basically. So what is the M value? The M value is a number we ascribe to the position of the slit in the pattern. So my straight through brightness, why will it be bright? Because you get a crest, it's equal distance, no path difference, constructive interference. I'm going to call that M equals 0. And that would be called your 0th order bright fringe. It's your 0th order. There's no messing with it. It's 0th order. M equals 0. And then the first darkness that you see above or the first darkness that you see below, just imagine this is cut in half, and don't worry about the bottom half particularly. It's just a repeat of the top half. This first darkness that you fringe, that you call, now what do we call it? First dark fringe that you see? We could call it the 0th order dark fringe. I have been known to call it the first order dark fringe, which is, I think, incorrect. In some of the homework questions, I call it the first order dark fringe. I mean the first dark fringe. I'd prefer to call that the 0th order dark fringe. And that is M and a half. And then we have the first order bright fringe and the first order dark fringe. That is 1 and 1 and a half. Second order bright fringe, second order dark fringe. 2 and 2 and a half. What the book says. The book says, okay, the book says only worry about the whole number M's, and if you have a darkness, add a half basically to it. The equation has a half in it. So the M is only 0, 1, 2, 3, 4, 5, and if it's a dark fringe, you have a half in the equation. And I just think, why not just call it 0, 1 half, 1, 1 and a half, 2, 2 and a half. Maybe I'm missing something, but I don't think so. So your job is, if I turn around to you and say the first order bright fringe, you can actually know which one I'm talking about. I'll try and be really clear on a test. I'll actually sometimes even point to it. So you can call it what you like, but that's the one I want. you know. But so you got to spend some time and get to know this terminology, and then you got to spend some time and satisfy yourself that we get constructive interference when the path difference is a whole number of wavelengths. Remember that? We did it with the two speakers. If it's a whole number of wavelengths, then crest number 13 arrives with crest number 12. But they're still crests, so we get constructive interference. And if it's an odd half number of wavelengths, so crest number 13 arrives with trough 15 and a half, I get a crest with a trough. So, you know, it doesn't matter which ones they are, as long as crest and crest gives you constructive, trough and crest gives you destructive. Yeah. So we've got to get kind of comfortable with that, and then satisfy yourself that, yeah, the path difference for this is 0, and then when it's a half a wavelength, I'll call it m is a half, and when it's one wavelength, I'll call it m equals 1, and when it's 1.5 wavelengths, I'll call it m equals 1.5, and so on. Yeah, so get familiar with that pattern. In a Young's double slit fringe experiment, what is the m value of the third order dark fringe? It's going to be third order, so it goes 0 for the first 1, 2, 3. There's my, and it always starts off by that. So my third order, this is my 0th order dark fringe, my first order dark fringe, my second order dark fringe, my third order dark fringe. It's going to be 3.5 wavelengths. Yep, m is going to be 3.5. Agreed? So 3.5 is 7/2. Okay? Okay? Let's go back and just see if I can. So this is my 0th order dark fringe, my first order dark fringe, my second order dark fringe, that's 5/2. My third order dark fringe will be 7/2. Yeah. Cool. In a Young's double slit fringe pattern, what is the m value for the second order bright fringe? Well, it's 0 for the 0th order, 1 for the first order, 2 for the second, 2 is 4/2. Agreed? Yep. So, got to be able to plug in the right value of m. This is conceptually what we're doing. So we basically have light, which is coherent, so the crest is lined up, but what's not lined up is the path difference, and so here it looks pretty good, but here it's kind of like a real issue. I'm actually bad drawing from me, actually. That's a bad drawing from me, because I'm actually starting, an observant student would say, this is out of phase with that. And it shouldn't be. It's not that that's causing the issue. It is the path difference. Yeah. So bad drawing from me, but just forgive me that and just recognize, oh yeah, they're no longer equidistant, so path difference effect. When the path difference is 0, crest arrives with crest, trough arrives with trough, constructive interference. I get a bright fringe. When there's an odd number of half wavelengths, that's half a wavelength or 1.5 wavelengths or 5.5 wavelengths, whatever. When the path difference is an odd number of half wavelengths, then we get crest arriving with trough, we get destructive interference, we get a dark fringe. Even number of half wavelengths, that's 2 halves, 4 halves, 6 halves, 8 halves, no halves is even. Then I get constructive interference, bright fringe. Yeah. So the two choices, well, if you take 0 as being an even number of half wavelengths, there's your two choices that we look at, yeah? We don't look in between, we just look at those two choices. Let's do some math. I'm going to assume that my screen is infinitely far away. Well, so far away it doesn't matter in terms of my angular measurements. That simplifies things tremendously, actually, because here's the overall picture. And I see two little slits, and I see a distance to a screen, and I see a direction of interest. I'm deciding what's going on at that direction of interest. Or I can turn and say, what what angle, where is my second bright fringe, something like that. Let's assume I'm pointing in the right direction, and I measure that angle theta. So it's that. It's on the bottom one as well, but I'm not going to draw it on the bottom one. It's on both of them, yeah, because it's infinitely far away. So the path difference, if you think about it, is this length here. It's from the further away slit to the beginning. You know, all the distance to the screen and the distance to the screen are the same. And again, you got to just. But hold on, if the screen's like that, then these two lines are the same length. But we kind of like cheating. We're really doing that because they've got to overlap in the end. But I want my math to be easier. So rather than saying there's two different angles here, I say let's pretend they're the same. Yeah. So it's not a finagling at the far end, it's a finagling at the near end. Okay, so there's my path difference. And my path difference is geometrically linked to the angle and to my separation between my slits. What I find is that my path difference is the R1, R2 minus R1, and R2 minus R1 is this little length there, which is d sine the angle. It's by trig, that's a right angle, d sine the angle. So I come up with this equation, m lambda equals d sine theta. For constructive interference, then m, we said, has to be an even number of half wavelengths, so m would be 0 or 1 or 2 or 3. And for destructive interference, m would be a half or 3.5 or 5.5 or 7.5, odd number of half wavelengths. This equation in different forms kind of keeps coming up, so it's an important equation. And what can I ask you? Well, I can tell you the separation between the slits. I can tell you the order or give you information where you can work out the m value. I can tell you the wavelength of the light, and then you can tell me the angle. Or I can give you the angle and ask you for the wavelength of the light. Or I can give you the angle and the light and ask you for the distance between the slits. There's only so much I can do with this equation. Your job is, can you figure out what m to write in? That's probably the hardest thing. And do you know that d is the distance between the slits and not the distance to the screen? So it's relatively simple once you get the view of it. It's a simple thing. There is a little step further, and that is, supposing I say, oh, let's just play with it a bit more. So rather than asking you for the angle or giving you the angle, I give you the distance to the screen and ask you for how far away from this central bit is the fringe that we're interested in. Is it millimeters or is it meters or what is it? So what's my y value? And in the book, what they do is they use a small angle approximation. They say, oh, tan theta is like sine theta, so we can just shove those x and those L and Y into this first equation. Problem is, that's realistic for light. But with the numbers I'm going to give you, you're not going to get a small angle. So I've had people in the past use a small angle approximation on an angle which is 30 degrees. And it's bad practice, and there's no need for it. It's not, the small angle approximation is an approximation. So why not just work out the angle, and if you want to know why, say tan the angle equals y over L, and do it as a two-step problem. So the small angle approximation, you know, it's one of those things where it finds its way into all the textbooks, and in the lab it's probably, you know, quite appropriate, but do you really need it? We know trig. Do we really need it? It's saving us 2 lines. You know, out of all the lines we write in our careers, 2 lines is not a significant thing. And yet it adds a complexity that you don't need. We know how to do trig, so just do trig on it. So do not use a small angle approximation, certainly for my tests, okay? So conceptually, some things, and you can see it from this. If for a given situation, if I make the slits further apart, so D increases. If D increases for a given fringe and a given wavelength of light, my angle, the sine of my angle must decrease. Because if the right-hand side is constant, the left-hand side must be constant. And if D goes up, sine theta must go down. If sine theta goes down, my angle goes down. So when you imagine moving these slits apart, you find that this pattern scrunches up on your screen. And if you imagine bringing these slits together, you find that the fringes open up. It's called reciprocal space. This is in the history and development of physics and engineering, this is a very important experiment for a whole bunch of reasons. But like a lot of things, it's just a very interesting thing. When you look at the history of science, you see these pivotal experiments. This is one. Another one is Rutherford backscattering, where they fired basically alpha particles into a thin foil of gold. The alpha particles should have just gone right through, but there was some backscattered, and it really shot down all the theories about what the atom was like. They had a plum pudding, or we'd call it an oatmeal raisin model of the atom, where the positives and the negatives were just mixed in together, and you can't get backscattered anything with that. It's like tissue paper. And by having these alpha particles bounce back, it meant they must be hitting something solid. Oh, all the positives must be dense. So that was the discovery of the nucleus. That in itself is incredibly important, and it's very interesting. But give it 50 years, and people are saying, hey, that phenomenon I can now use as an analytical tool. Because I can look and see how does the alpha particle bounce back, and I can tell you about the nucleus. The same goes with this. This phenomenon can actually be used because, man, you want to analyze the wavelength of your light. We can use this as an analytical tool. And you can go even further, actually. Basically, this is slits in a screen. Supposing I had a reflection, supposing I've got grooves on a metal plate, I can get the same effect by reflecting light from it. And that's an alternate way of doing this experiment, by the way. You actually make a metal plate with grooves on it rather than having a film with holes in it. You know? If grooves on a metal plate can do this, then what else can reflect wave-like things? Well, it turns out, if I say instead of using photons, let's use electrons, the only difference is the wavelength is a lot less. And instead of using slits, I use atoms. I can use this same technique, and I can take what's called transmission electron microscope images of a lattice. And I don't get a picture of the lattice, I get an interference pattern, if you like, of the lattice. And if the atoms are close together, the spots that correspond to those layers are far apart. And if the atoms are far apart, the spots that occur close together. So this is the underpinning of crystallography, basically, finding out what your electron structure is. There's so many layers of analysis come from things like this. So, and they're whole fields in themselves. You can spend your entire career being an electron microscopist, transmission electron microscopist. And I've seen them, and it's amazing. They look at the pattern, and they think, and they're building three-dimensional pictures in their brain based on that. And so it's called reciprocal space. So a very important equation, and know how to use it. That's the key thing on that. So here's an example. I guess I started doing some of these things, I guess this was before we had the videos and the like. So basically, let's do a problem. Consider the young slit apparatus. The two slits are separated by 500 nanometers. 100 nanometer light is incident on the slits. So first question, what angle will the second order bright fringe make to the optical axis? So here I'm sorting out my order. So my 0th order is straight through. My first bright fringe is at m equals 1. My second order bright fringe is at m equals 2. I know that m lambda equals d sine theta. My m is 2. I just decided that. And my lambda, the light, is 100 nanometers. I'm leaving it in nanometers because if I stay in nanometers, I'll be all right. Nanometers divided by nanometers is okay. Meters divided by meters is okay. Nanometers divided by meters is a problem, you know. So I can leave it in nanometers. If you like, just put down the times 10 to the minus 9. And then equals d, and the separation between my slits is 500 nanometers sine theta. So let's have a look. That's going to be sine theta equals 200. Sorry, I missed out that 2. 200 over 500, which equals 0.4. So you go to your calculator and you go theta equals sine to the minus 1.4, which is 23.6 degrees. So I found my first thing. Just in a way, it's mathematically it's a piece of cake. It's just knowing what you're doing and why. The second part says if the screen is 3 meters away, how far will the second order bright fringe be above or below the optical axis? I'm showing above, but it's symmetrical. So we say, okay, there's my y, there's my L. Tan theta, tan that angle equals opposite or adjacent y over L. So y is equal to L tan the angle, which would be 3 meters. Can't find my 3 meters. 3 meters times tan 23.6, which is 1.3 meters. These things, you know, there's so many things wrong with the scale of these numbers. These things are tiny to see on a screen that's a fair bit away. So, cool. Okay. So first set of problems, Young's double slit. It's very important. It's a very important equation. You know, this is important stuff. Got to do a next little bit, and I want to remind us of something. And so, do you remember those videos we showed where we had a ripple going along a medium, and basically sometimes it bounced back. What was a crest bounced back as a trough when this end was fixed, and other times when this end was loose, what was a crest came back as a crest. And we said, well, what this corresponds is to a flipping. It's almost like your wave's going along, and then suddenly at this point, it, rather than continuing, it flips. It goes from a crest to a trough. That's what it's doing here. It's flipping. So it's almost like you jump ahead. Or jump behind, doesn't matter. A half ahead is the same as a half behind because everything's repeating. But in this case, it doesn't. You know, and there was some interest in, well, that's interesting for strings, mechanical systems, it's interesting. We saw it with the waterbed versus the waves at the swimming pool. The waves at the swimming pool do this. If you do a crest going to the wall, you get a crest coming back. But if you jump on a waterbed mattress, what goes as a crest comes back as a trough. It's the weirdest thing. So, okay, that's kind of cool. Electrical signals in coaxial cables. You'll get some reflection from the connector. Now, depending upon how well you make that connector, sometimes you'll get it bouncing back in phase. As a crest comes back as a crest. Sometimes it will bounce back as a trough. Crest comes back as a trough. Very different outcome. You're interfering with the signal that's coming in two different ways. Ideally, you'll make it so that the impedance of your connector is exactly the same as the impedance of the wire. and the electrons won't even know they're going through a connector. Then there's no reflection. So a badly made coaxial cable will interfere with the signal that's trying to go through it. It'll bounce back and interfere. So that's why you can't have a coaxial cable connected going 50,000 miles. It's kind of like, you're going to lose signal. Okay, and optical fiber cables, somehow you've got to connect these things together, and again, you're going to get this, it's reflecting or is it not reflecting? If it's not reflecting, how is it reflecting? And we see this effect actually in lots of different ways. So here's a picture. When I was a kid living in England, where you get grey, sometimes relatively bright, but you get grey skies, and you get dark architectures. The whole place was covered in soot. When people talk about pollution, we really are victims of our own success. Because for my generation, pollution is really real, and it's miserable. People coughed their lungs up. People died of it. Not just those who were doing dangerous jobs, like down a coal mine, although a lot of those people died very young. But people who just lived in those communities. In something like 1953, there was a weather inversion over London, and 5,000 people died. I think it was in like a 2-week period. And it was huge. And it was because all the fires, for most of until I was about 14, we had a coal fire. It would just burn coal. Every household. You knew if people were in if there was a smoke coming out of the chimney. It's like, are they in? Now we look at is the car in the driveway? For my generation, look, there's a smoke coming out of the chimney. If smoke coming out of the chimney, you can go and knock on the door and say, does Johnny want to come out and play? If there's no smoke coming out of the chimney, they're at work. And it's like, so given those circumstances, you tended to get, everything was covered in grime. You got this grey but evenly illuminated sky, and you got oil all over the place because pollution was also leaky car engines. Weren't many cars, but you could smell them before they hit you, kind of thing, because they leak like sieves. And you get these droplets of gasoline or oil, and you just see these iridescent colours, and it's kind of fascinating. I just remember as a kid just spending a long time looking at these things. We see the same thing with bird plumage. They're using kind of the same process, bird plumage. You get these colours that are not caused by pigments. They're caused by basically the reflection of light. And it's done by thin films, transparent thin films. And what happens is, have you noticed, how many people have seen something like that iridescent thing? I should try and set up a demo for this. We could do it. Set up a demo and have you look at it. Because a lot of people have never seen it. If you change your angle to it, the colours shift, yeah? They're not painted on. Just like if you get a bird's wing and you change your angle to it, the colours shift, yeah? Butterfly wing, same thing. It's like, well. So, remember those cars? It was all popular. There's a few trends in cars that I really liked. The day glow lights like underneath the car. I just thought that was the coolest thing driving around. And I wanted to get it done to my car, and then I was teaching at the time, it was like 45, 47, 42. And I said, oh man, one of the kids in class said, you have those, like, what colour are they? Oh, they're green. Oh man, where'd you get them from? And then one of the students said, you're too old. And the other thing from what I gathered is if you had those lights, the police would just pull you over because you were doing something, it's like So I wanted them. The thing I never wanted, that I never understood was, the car that has the two colours of, you look one way, it's a green car, and then you go down here and it's a blue car.
Yeah, perhaps, yeah.
I mean, I don't think in Britain that would be allowed. Because in Britain, I emigrated and got my citizenship. In Britain, they have number plates
which are big and very readable. They're like made to be seen, because the idea is if somebody's doing something wrong, you should be able to look at them and get the number very clearly. How many times have you been driving down the road and you can't even read the number plate of the car that's in front of you? It doesn't identify anything. It's like, well, you know, that they support teaching, but you can't read them very well. And anyway, so getting off and off. So anyway, I mean, a car that can change colours depending on how you look at it, seems to me like it's the kind of thing that the Joker would have rather than Batman, you know? It's kind of like... So the angle matters. And what's going on here is you have a thin film and you have white light coming in, all these different colours of light, and you're getting some of the light, lost my pen again, some of the light is reflected from this top surface, and some of the light goes through the film and is reflected from the bottom surface. So there's a path difference. And then in your eye, the two beams cross, that's how you form an image, and maybe one's a crest, maybe one's a trough, and they cancel each other out. The reason why you see these different colours is because as you go to different angles, you get different effects. And in this point here, the green light has just the right wavelength to give you a constructive interference, but the other colours don't. And out here, the red is just the right wavelength to give you constructive interference, but the others don't. And if you see, it repeats, doesn't it? There's red. I bet if I go in here I can find red. And that's what's going on. First order, second order, third order, fourth order. And you're working your way through the colour spectrum. We'd like to analyse this for a whole bunch of reasons. And so we're not going to take white light, because that's complicated. We're going to take a monochromatic colour of light. And we're going to say, what thickness of film do you need to get the first brightness, or the second brightness, or the third brightness, or the third darkness, or whatever, for that colour. Okay? So we've got to analyse this. Interference is about path differences, yes. But interference is about path differences and reflection when the path difference is caused by reflection. So this is a little bit more complicated than Young's double slit. It's got this reflection effect taken apart. And we have two reflections. We have reflection from the top surface and we have reflection from the bottom surface. And the key question about reflection is, do I get a phase jump or not? And do you remember how we had the thick string and the thin string, and you know, we got a different answer depending upon whether we had the thick string. If the energy was going that way, if the energy going that way, in one case we got reflection that was out of phase, in the other case we got reflection that was in phase. Yeah? Remember that? It's in your notes, I think. Same kind of thing here. What matters is the optical properties of the two mediums, the one you're leaving and the one you're entering, or the one you're reflecting from, really. And so what you learn, and I think the best way to learn this is to picture something. So I want you to picture standing outside a store which has thick glass. You know, stores have thick glass. And how many people have seen when you on a night when you stood outside a store, certainly if the store's lights are turned off and you're stood in the street, so you're illuminated, and you look at the reflection of yourself, how many people have seen two reflections of themselves? One from the front face and one from the back face. You can sometimes see it. Okay, so you have two reflections. When you get reflection off of a medium which has a bigger end than the one you're in, then you get a phase jump. So let me put a page in here. So let's think about this. 3, come on, 3, there's a number of possibilities. I'm going to say n equals 1, n equals 2, n equals 1. That's like air, glass, air. There's n equals 1, n equals 2, n equals 3. That's like air, glass, diamond. There's n equals 3, n equals 2, n equals 1. That's like diamond, glass, air. There's n equal 2, n equal 1, n equal 2. That's like glass, air, glass. Don't worry about the numbers, just their relative size. Doesn't matter, it's 1 and 2. Could be 1 and 1.3. Doesn't matter about that, yeah. Just, is it going up or is it going down? Reflection. Reflection, there is a phase jump because I'm bouncing off something which has a higher refractive index. Reflection. There is a phase jump because I'm bouncing off something which has a higher refractive index. There is a phase jump because I'm bouncing off something that has a higher refractive index. Reflection. There's not a phase jump because I'm bouncing off something that has a lower refractive index. Let's do all the tops to begin with. So, bounce off something high refractive index, you get a phase jump. Bounce off something high refractive index, you get a phase jump. Bounce off something low refractive index, you don't. Low refractive index, you don't. Do I get a phase jump or not? I'm bouncing off something of low refractive index, so I don't. Do I get a phase jump or not? Yes, I do. I'm bouncing off something with high refractive index. Do I get a phase jump or not? No. Do I get a phase jump or not? Yes. I'm comparing these rays. So what matters is the comparison of their histories. This one has a shorter path, this one has a longer path, so the path difference matters. This one had a phase jump, this one did not. So this is a half a lambda because of a phase jump. That's the effect of that reflection. This one had a phase jump, but so did this. I'm comparing these waves. I'm comparing the rays. No phase jump. Let's do effect. Because there is a phase jump in both places, but they cancel each other out. Because I'm comparing. No phase jump effect. Phase jump effect or not? Yeah. Half a lambda phase jump effect. So this is air, glass, air. You get a phase jump effect. This is glass, air, glass, phase jump effect.
Wouldn't that one be one, like the second one be a full phase?
No,
What's the lineup?
because you're comparing them. So if I jump ahead and you jump ahead, we're in step again. So, good question though. Now it doesn't have to be symmetrical, it doesn't have to be air, glass, air. As long as, you know, if it was n equals 1, n equals 2, n equals 1.8, it would still be yes at the top and no at the bottom. So it's just the difference. You've got to ask it. I think it's really useful to remember this by picking one and getting the principle out of it. So that's the one that I pick, which is air, glass, air. And I know I get a out of phase. I get a phase jump because of the first layer and not because of the second layer. So I know I've got to take it into account. And then I can figure out the rest from there. Okay, so the way you do these is you say, what do I need to get the fringe that they're talking about? The brightness or the darkness they're talking about. And the next question is, do I have a phase jump? If no, ignore it. If yes, take it away from what you need. What's left must be done by path difference. Final wrinkle. Refractive index means that you're changing the wavelength of the light. If I need so many wavelengths path difference in the film, that physically represents so many wavelengths of the light in the film, not the light out of the film. Films, big refractive indices tend to reduce the length of your wavelength. So it's not, if I need 1.5 wavelengths for the path difference, it's 1.5 wavelengths of the light when it's in the film, not the light when it's approaching the film. So I've got to take that into account. So what we say is we see vivid colours when light shines on thin films. These are caused by interference. There is a phase change of 180 degrees upon reflection. If the reflecting medium has a higher refractive index than the medium which the wave is travelling, and the wavelength of light in a medium whose refractive index is n is given by lambda n equals lambda over n. You divide the wavelength by its own refractive index. Remember that the refractive index is the ratio of the velocities, and if the frequency is the same, it must be the ratio of the wavelengths. So it's lambda over n. 3 bits. So here's, and again, I guess I might get rid of all these because I like to do them. It's got swings and roundabouts actually. It's kind of like, anyway. 300 nanometer light is incident upon a soap bubble. So now we're talking about a soap bubble. Okay, air, water, air. How thick a film will cause second order brightness? Okay. And N for soap is 1.6. So what we say is for second order brightness we need, well, 2 wavelengths. Agreed? That's what I need. So these two must be 2 wavelengths apart in terms of not just path difference anymore. Path difference and phase shift. First thing I ask, do I get help because of phase shift? Phase shift. There is a phase shift of lambda over 2 at the interface A, but not at B. So there is a phase jump. So I'd use it, I'm kind of trying to be clear with myself. Phase shift is what happens. Phase jump is the effect on the system. Yeah. So there is a phase jump effect, if you like, upon reflection. Because I go little, big, little, I'm going to get half a wavelength phase jump. I needed 2 wavelengths. I got half of it already. So that leaves 1.5 wavelengths. So this leaves 3 over 2 lambda from the thin thickness, So then you look at it. It's tempting to try and do some trig on this, but, we're just going to say it comes straight in and goes straight out. So 2t, 2 times your thickness, is equal to 1.5 wavelengths, so 3 over 2 lambda. But the lambda is not the lambda of the light that's incident. It gets reduced by the refractive index of the material. So we say, but lambda inside the film is not the same as lambda in the air. Lambda in the film is lambda in the air divided by the n of the film. So 2t is going to equal 3 over 2, not lambda, but lambda over n. Because this is the lambda inside the film. This is the lambda, this is the lambda. The lambda that we need is the lambda inside the film. Well, rearrange. T is equal to 3 lambda over 2 n times 2. Took that 2 and put it down here, which equals 3 lambda over 4n which equals 3 times the original lambda in the air, which is 300 over 4 times 1.6, which gives us that. And that's the scale. So what would I do in a question like this? I would give you a different value. I might turn around and say, the third brightness. I'm going to avoid darknesses, because that leads to confusion. And I can do that. I can tell if you got the basic idea of this using brightnesses. Okay. So what would the overall effect be for a first brightness? How many wavelengths would I need for a first brightness? 1. And then for the second brightness, third brightness, fourth brightness. So you got that. Then the next thing is, if it was air, water, diamond, phase shift effect, air, water, diamond, phase shift effect? No. If it was water, air, water, phase shift effect? Yes, it's when you go up and down, or down and up, you get the phase shift effect. And then the next thing is, work out what your wavelength, work out how many wavelengths you need, and remember you can't use the wavelength in air, you've got to use the wavelength inside the film. Yes?
So is the 2T because it gets reflected through, does it go through twice?
Oh, don't go through twice. The first T, is it going down? The second T, is it going up?
Yeah, that's 1, 2.
Yeah, yeah.
Okay, so twice?
Yeah, it's like from here to Orlando and back.
Okay.
So it's like, it's not just the distance from here to Orlando, it's back again.
So that's where the 2 comes from.
That's where the 2 comes from, yeah. Cool. So, yeah, cool. Let's have a look. 51. This is actually, I'm kind of, in a weird way, I'm kind of proud of this picture because I guess my energy's been taken up by making sure the videos are working, whereas in past semesters I've done a lot more demos actually. I got to merge the two. But this was actually taken here using basically a camera on this thing. And what happens is we take like a lens and we take a piece of glass, and so we have a little air gap. And this is like right there. It's like just that little bit around there, and you look through and you see it. And what you see is a whole pattern of dark and bright fringes. And you can see that, you know, that's quite broad, and that's not as broad, and that's not as broad, and that's not as broad. And that's literally the curvature of the lens. It's how the air gap is increasing as you go, and the rate of increase. So you can look at this pattern, and you can do basically calculations to determine what the curvature of that lens is. And in fact, when they're making mirrors, there's a astronomy club in St. Petersburg that used to have, I think it still has, but they used to have a mirror making facility. You get it by hand. You basically get a pillow and you rub and you do, 6 months later you have a nice mirror. And you work on the averaging. It's like, one little swirl will not give you a spherical lens, but 2 million will average out all the bumps, and you'll end up with something quite nice. But you can check it, and you check it using an optical technique, and they get a pattern like this, and it can tell you the curvature of the thing. So if you're asymmetrical, if you're doing that, you've got a problem over here, and you've got to keep on polishing. This is another example. It's not. No, that is a picture. Yeah, that's another one of our pictures where basically we have 2 glass slides, and basically we're shining light on, monochromatic light, and we're seeing that we're getting. Now think about this. Between there and there, there's 1 wavelength, and that means the gap is half a wavelength. So we're measuring. Our ruler is calibrated in half wavelengths of light. We're using light as our ruler. Now, blue light, okay. Let's go to ultraviolet light. Let's go to, and so on. You can get tremendous effects from this. There's a thing so they use optics to measure distances. It's really quite precise, and if the light is not precise enough, change the colour. So if you think about it, when you make semiconductors, you use masks, these opaque masks, and you shine light through. And that light causes the polymeric protecting film to polymerize or not, then use acid to wash away the bit you don't want, and then you chemically process the bit that's uncovered, and then you strip everything off and you do another pattern. That's how you build up your semiconductors. And whenever the geometry is big compared with the wavelength of light, no problem. Little edge effects, but you can live with those. The sales department wants more and more on less and less chip. So they're always pushing to make the masks smaller and smaller. And as you get smaller and smaller, you get to the stage where these effects are more and more significant. So what do? You change the light source. So if you can go to a smaller wavelength, the features that you're building are relatively big again. So these effects diminish. And so whereas in my day, you used just visible light as your exposure light to expose your photoresist. Now they'll use ultraviolet light. They'll get short wavelength as they can to make finer and finer features, to get more and more memory onto a small chip. And they're fighting that battle. The life in a semiconductor fab is, I think, very hard, because it's all about money and real estate. It's all about what you can do with a chip.